All right, welcome back, everybody. We're going to continue with 13.3. So let's just relook at that statement, the fundamental theorem for line integrals. Now, if you look at this, you might be tempted to think, just from this statement, that the integral of a vector of this sort of thing, this is actually a vector field, right? Caused by or a gradient field, sorry. Okay. Doesn't depend on the way you get there, right? So you could have gone this way, this way, this way. Well, I mean, it's still okay because it still was somewhat smooth. I could just go any way I want. Man, I love this thing. All right. And that's true up to a point. So we're going to talk about what that means. So that statement is called path independence. Let's type it out. Path independence. Let me get my keyboard. Under certain circumstances, and we'll talk about what that certain means, the line integral of a gradient vector field does not depend on the path it took to get there. Okay, makes sense actually. Once after a lot of years of thinking about it, it makes sense. Okay, so before we really investigate this more, we're gonna have to define a couple of things. Okay, so we're gonna have to define first an open set or an open region. Okay, I'm going to put make the definition. We'll talk about what that means. So, a set, let's call it D in the plane, is open. That's what we're going to define. Okay. If given any point x comma y in D, there is a arbitrarily small circle around xy that is completely contained in D. Okay. So, let's expand on that a little bit. So, we're talking about open here. Okay? So, let's start with in college algebra. Let's go back to college algebra. In college algebra, you learned that AB does not include the endpoints. Okay. While A comma B does include the endpoints. Okay, so if we draw a number line here, and we put, let's say, A here, oopsie daisy, we put an A here, and we put a b there, then it doesn't matter where we pick a point, but if we pick a point here, okay, let's call it x, all right, then I can put a little interval around x. We call it actually an open ball. We'd say, this is where you start seeing epsilons again. You may remember epsilons from Calc 1. Okay, so this statement here there's an arbitrarily small circle around xy that is completely contained in D. Okay, we're going to talk about that statement here. So if I do this in 2 dimensions, if I wanted to talk about this in 2 dimensions, then I could have, like, let's say, oh, let me actually undo that because I want to make it open. So I'm going to have a dash lines, and I can put, let's say here's xy. xy has to be away from the boundary, and I can make a little circle around it with radius epsilon. So the language that you'll often see here for that is, this is the same thing as this language, but it's going to be in a little more mathematical terms, is that D is open if for all x, y in D, there exists epsilon bigger than 0 such that the open ball of radius epsilon centered at xy, so this is equal to, this is a set, this is the x prime, y prime, so that the distance, so we're going to write it as x minus x prime squared plus y minus y prime squared square roots. Now let's get rid of the square roots and instead say that's just less than epsilon squared. Okay, so that this set is contained completely in D. Okay, so that's what this is saying. That's the language that goes with this. Okay, so that's how mathematicians would say it. Okay, so you're going to see, if you go further in math or what have you, even in engineering, you will likely see this language again. And this is a very common language for that. Okay, so that's all it's saying. So that's one of the concepts we're going to need, or one of the concepts we're going to use when describing this path independence. Okay? Next, we're going to talk about a connected region. Okay. A region D is connected, okay, and I want my region to be in the plane. All these concepts do expand to like space and higher dimensions, but we're just doing it in the plane right now. Is connected if given any 2 points. Let me move this. xy and x prime y prime in D, then there's a path in D, completely contained in D, connecting them. Okay, so let's sort of draw a picture of what that means. All that really means is that if I have some region, maybe I have a point here and a point here. So that's xy. This is x prime, y prime. Then all I have to do is I have to just say there's just some way to get there without leaving D. Okay, so that's all it means to be connected. Okay, all right. We'll come back. We'll do a little more theory on the next video.